Hello everybody, welcome to this massive open online course on fluid flow operations. In this lecture we will discuss one dimensional flow as a part 3. Here we will discuss the principle of conservation of momentum. In the previous lectures we have discussed other basic equations of fluid flow like mass conservation and also energy conservation equations. In this lecture, we will try to cover these principles of conservation of momentum, which is called momentum equation. And in this case, of course, you will see when this momentum will be existing. Let us see that if any flying baseball, if it is caught by you, then what will happen? There will be a certain change of momentum on your hand whenever baseball will fall in your hand. Even you will see whenever we are driving that automobile. So, when it will be moving and if you see, if we suddenly stop that automobile, it will be very difficult to stop at a very short time. So, in that case, due to its momentum, the automobile cannot be stopped immediately whenever you stop your start there. So, there will have some momentum by which you can go further for a while. Therefore, in this case to represent this momentum, you will see we cannot only consider the velocity there, this momentum effect of this other factor that will give you this momentum. Now, like mass, if suppose heavily loaded that automobile, then what should be the momentum, how it can be produced. You will see heavily loaded automobile will have more momentum if it has the same velocity, and also if suppose the lighter body will have the same velocity, it will have less momentum. So, how can we represent this momentum there? If we multiply this mass of the body by its velocity, it will be considered as the momentum. But what should be the change of momentum with a short period of time? If suppose velocity, if you are changing suddenly from original to another one, so there will be some change. Now, if we have the velocity at initially, it will be let it be what is that initially it will be v1, and after a certain time, if the velocity is changing to v2, then what should be the velocity change? v2 minus v1, and in that case mass will not be changing for the same mass of body. If we change this velocity from v1 to v2, then we will have the change of momentum. Initially the momentum is m v1 and finally the momentum due to the velocity will be m v2. So, the change of momentum will be m v2 minus m v1. Now, if this momentum change with respect to time with a short period of time t, then change of momentum, or you can say increase of momentum or decrease of momentum based on the velocity, that will be equals to momentum going out and the momentum coming in. What should be the increment per unit time. So, in this case we can say that the velocity, it will not be the sufficient to represent this body motion, but product of this mass and velocity can be used as an indicator of the consequences of the motion of the body, and this is called the linear momentum. By Newton's second law of motion, the change per unit time in the momentum of a body, which will be equal to the force acting on the body. So, the momentum, increase of momentum can be represented by the force acting on the body. So, force will be equal to then m v2 minus m v1 divided by t, as it is given in this equation here in the slide. So, momentum change will be equals to f, that will be equals to m v 2 minus m v 1 by time t. So, in this way we can easily calculate the change of momentum by this equation. If we know the velocity and the mass, then we can easily calculate the momentum. So, this is linear momentum, because there is no change of mass of the body whenever it will be changing its velocity from one to another. If suppose any momentum is having that mass and velocity both will be changing, then it will be non-linear momentum. Like suppose any liquid is thrusting on a inclined surface. In that case, you will see that liquid which is thrusting on the inclined surface will be divided into two parts. One part will go downward along with the surface, another will go up again along with the surface of the body. So, in that case you will see the mass will be divided into two parts. Similarly, the velocity at which the fluid mass will be thrusting on the solid particle or any solid surfaces, the velocity will be changing accordingly. So, in that case both mass and velocity will be changing, and due to which we can say that momentum also will be changing accordingly. So, in that case it will be non-linear, because both will be changing there. And also you will see some other cases, there will be some angular velocity change, and because of which there will be a momentum change in the angular direction. So, we will be discussing here in all the cases, and also where the momentum change will be applied, with examples we will discuss here. Now, let us see one derivation for this, how to actually represent this momentum here. Let us consider this fluid element as shown in figure. Here see the fluid is moving through this control volume or through this pipe that is bent, and here, and due to this moving of the fluid through this conduit, there will be a certain change of pressure from this section to this section, AB section to DC section, and in this AC sections the velocity of the fluid is V 1, and at section 2, that is in the DC sections, the velocity of the fluid is V 2, and a cross sectional area of both the sections are A 1, A 2 respectively. And due to this movement of fluid at these velocities, you will see there will be a certain momentum exerting on the surface of this conduit, and equally the same momentum will be exerted by the surface, so that there will be a balance of these two forces. And of course, you have to balance these two forces. If it is working in the several directions, then you have to consider the balance in the several directions. Now, if we are considering these things, suppose x and y directions here in the two dimensional cases, if suppose f x and f y are the component of forces in the x and y directions of force F respectively, then from the equation of momentum we can write here this minus f x at this moment here. Suppose this is the momentum force acting over this. So, here this x direction, this is y direction. In the x direction, what will be the force acting on that, or here what will be the x direction forcing acting on that. So, it will be minus f x. In this direction, the momentum will be acting opposite to the fluid motion here by this surface. So, minus f x will be acting in this direction, minus f x plus what will be the other forces acting over this surface here. It will be, what is that, A 1 P 1, P 1 is the pressure at this point, into cos alpha. Why? because this element is this in the x direction, the fluid motion is there at the direction which you will be making an angle of alpha 1 with respect to horizontal axis. So, in that case plus A 1 P 1 will be acting, that is A 1 P 1, it is the force, and in the x direction it will be cos of alpha 1. And again in this surface here the fluid motion will be in the direction of alpha 2 with the horizontal. Then we can say the force acting in this direction will be A 2 P 2. Now, in the x direction what will be the force over here? It will be A 2 P 2 into cos alpha 2. So, this A 2 P 2 cos alpha 2 will be in the negative direction. Okay. So, what will be the force? Effective force here minus f of x plus A 1 P 1 cos alpha 1 minus A 2 P 2 cos alpha 2. That will be equal to, what is that? Mass into velocity change, that will be your momentum change. What will be the momentum change here? Mass into velocity change. Mass is what? Here in these sections mass will be equals to what? That is the same, and here at this section what will be the mass? This will be same, because mass conservation will be following their mass flow rate. So, this will be mass flow rate, and then V 2 in the x direction what will be the V 2? Simply V 2 into cos alpha 2, here V 1 in the x direction what will be the velocity, that will be V 1 cos alpha 1. So, this will be acting in this direction negative of x direction, here also it will be acting here in this direction x direction. So, in the x direction positive x direction. So, velocity change will be V 2 cos alpha 2 minus V 1 cos alpha 1. So, this will be your momentum change per unit time. So, in this case you can easily balance on that by this equation number 2. Similarly, in the y direction, if we consider this momentum change, it will be minus f y again plus A 1 P 1 cos sin alpha 1 minus A 2 P 2 sin alpha 2, that will be equals to m into V 2 sin alpha 2 minus V 1 sin alpha 1. So, in this case if we simplify these two equations by taking the mass conservation equation here, like mass will be m will be equal to rho q, rho is the density of the fluid, q is the volumetric flow rate of the fluid. So, rho q will be equal to mass flow rate, and then rho A 1 V 1, that will be equals to what is that mass flow rate, and here rho A 2 V 2 in these sections, then it will be your flow out at this DC section. So, that will be equal to rho into q. So, here we can say that mass conservation law, that m should be calculated like this. Now, if we substitute this value in equation in this above momentum equations here, so we can simplify it. F of x will be equal to this and f y will be equal to this, and from this f x and f y, what should be the effective force or resultant force will be acting by this solid surface to balance this fluid momentum here. So, this will be equal to what? F will be equal to root over f of x square plus f of y square. So, this will be your resultant force. So, what force will be acting based on the momentum equation, we can easily calculate in this way. Now, let us have some applications of the equation of momentum here. Now, if we consider that what should be the force of a jet, if any jet is emerging on a solid surface, then what should be the force acting on that solid surface by the jet, and also how this solid surface will be balancing by exactly equal amount of momentum on the fluid. Similarly, other application like you can apply this momentum equation to calculate the loss in a suddenly any expanding pipe. Sometimes in the real fluid, real operation, we are having some operations in such way that you have to supply some fluid from the narrow tube to the coarser tube or coarser tube to the narrow tube. So, in that case, if we supply some liquid from the narrow tube to the suddenly expanding pipe, in that case you will see there will be some loss of energy, and you have to calculate that loss of energy by this momentum balance equation. Again, how this momentum or force will be calculated by this momentum equation for the jet pump, and also what should be the efficiency of the propeller, that can be calculated by this equation of momentum. Let us consider this force of a jet on board at rest. Here see this yellow color, this one, this is called a board, flat board, and in this flat board the liquid is coming from a source, from the pipe or from a jet, and it will be coming and it will be thrusting on this board at a certain velocity, at a certain flow rate, and whenever it will thrust or push on this board, the liquid will be divided into two parts as a Q1 and Q2. Similarly, the velocity also of this fluid will be changing in these directions, and if we apply this velocity here or flow rate in this direction, accordingly the force will be acting over this body point here, and the force acting on this body will be in this direction perpendicular to this board. Now, this perpendicular to this board, you have to have this force component whenever it will be exerting on the fluid mass. So, that you have to calculate, that will be your force, that will be F, that you have to calculate it. Now, how to calculate this? You have to do the momentum balance here. So, in this case consider two dimensional jet that will strikes on the inclined flat or board, you can say, at rest, and it breaks into the upward and downward jets. Now, in this case the velocity of the jet turns out to be 0 at this point, after it has struck the flat board at this point at a velocity of v into sin theta. Why? Because the velocity in this direction is, if it is considered in this direction, then this will be your x direction, but perpendicular to this direction what should be the velocity, that will be equal to v sin theta there. Now, then what should be the F there? This force will be nothing but this force, this in this direction this fluid will be acting, and opposite directions as per Newton's third law, the same force, equal same force in the opposite directions will be applied by this flat plate. So, this F should be equal to what is the velocity or what is the flow rate, that is q of the fluid. So, rho into q, that will be your, what is that, mass, and into velocity v into sin theta, this will be your momentum, this will be your velocity. So, momentum will be equal to what, that will be the rho, what is that, q v sin theta. Okay. So, mass into velocity. So, this will be your momentum. Now, if it is coming from the 0 velocity, then momentum change will be equal to rho q v sin theta minus here 0. So, it will be equals to rho q v sin theta. Similarly, this force balance to be done in x and y direction. In the x and y direction, the components of this fluid momentum, or this will be F, this F component will be divided into two parts in the x direction and y direction. So, in the x direction the components will be f x, and in this y direction it will be f y. So, f x will be equal to f into sin theta, because this is your theta. So, f y will be equal to f cos theta, and this will be your what is that sin theta. So, f x will be equal to f sin theta, that will be equal to, if we substitute here the value of f, we can get rho q v sin square theta. Similarly, f y in the y direction, it will be coming as f into cos theta, that will be rho q v sin theta into cos theta. Now, interesting that what should be the momentum change in this particular direction here, what will be the momentum change. Now, it will be rho q v sin theta, because v is acting over here in this direction. So, v sin theta, it will be your v cos theta. So, rho into q into in this direction, it will be v cos theta. In this direction, what will be the momentum? So, this momentum will be given by this flow of fluid at flow rate q. Now, this will be effective in this direction. So, in this direction, what will be that v into cos theta? If we see that, it will be your rho q v cos theta. So, that will act in this direction, where the component of flow rate will be flowing upward along this flat plate. Now, what will be the effective then momentum, what is acting in this direction? If we consider that flow rate is divided into two parts, q 1 and q 2. In this q 2, what will be the fluid part? This is q, this is q 1. In this direction, this will be your q 1 fluid mass. So, rho q 1 v in this direction, it will be there, minus rho q 2 v in this direction. So, this will be your what is that change of momentum whenever it will be changing in the divided into two parts, because this momentum here, the energy will be the same there, this, because this one and this one. Okay. So, this will be subtracted, this will be divided into, and then ultimately from this balance you can say that q into cos theta, that will be equal to q 1 minus q 2. Now, from this momentum equation and also from the mass conservation of equation, that means q will be equals to q 1 plus q 2, then you can have, after solving these two equations, what should be the q 1? Q 1 will be equal to q into 1 plus cos theta divided by 2, whereas q 2 will be equal to q into 1 minus cos theta divided by 2. So, by this equation 9 and 10, we can easily calculate from this momentum balance equation what should be the q 1 and what should be the q 2. Once we know the flow rate of the fluid at which it will strikes on the flat surface, which will be inclined at an angle theta. So, by this equation you can calculate the thrust or force acting by the liquid jet on the board. But this is applied only the condition that board will be at rest. Let us do an example for this. As shown in this figure here, now a jet of water of flow rate is q and diameter d that strikes a stationary plate at an angle theta here. Now, calculate the force on this stationary plate and its direction, so that the theta is measured and which will be found at 60 degree, and diameter of this jet is given 25 millimeter, and flow rate of the jet is given 0.1 meter cube per second, and then find out what should be the q 1 and what should be the q 2, and also what should be the amount of force acting by this fluid, and to balance this how much force is acting oppositely by this plate. So, that will be your F. So, first of all we have to calculate what will be the velocity of the jet. So, velocity of the jet you can calculate from the flow rate and the cross sectional area of the jet. So, here the cross sectional area is given to you A and the flow rate is q. So, q by A, that will be your jet velocity. Now, F is as per that previous slides that we have shown that the F should be equal to rho q V into sin theta. Simply you just substitute here, rho is given to you, q is given to you, and what is that? Rho q V now you have calculated here, and what is that? Sin theta, theta is 60 degree. So, finally, after calculation you are getting the F value 25405.23 Newton. Similarly, we can have from those equations of 9 and 10, what should be the component of this flow rate, that is q 1. So, q 1 will be equal to then substitution of this theta and q value in this equation, then you can get 0.09 meter cube per second, and q 2 will be equal to q into 1 minus cos theta by 2, that will be equals to 0.03 meter cube per second. See here, the summation of this mass will follow the conservation of mass equation. So, in this case this will be summation, that will be equals to what? 0.12 meter cube per second. So, in this way we can solve the problem whenever any liquid jet is thrusting or striking on a inclined rest board or plate. Now, the case where the board now is not in the resting condition, it will be moving in the same direction at some other velocity. Now, in the case where the flat board, it is shown in the figure here in the same direction, if it is the board is flowing in the same direction at u velocity, then what should be the effective mass that acts on the surface of the board. So, that you have to calculate. So, here in this case fluid velocity is v and also the board velocity or flat plate, you can say the velocity if it is u, then from that from this equation, the equation number 11, you can calculate what should be the effective flow rate reaching the flat board. In this case the effective or relative velocity is v minus u. So, q dash divided by v minus u, that will be equal to q by v. From that equation you can easily calculate what should be the q dash here. So, q dash will be equals to here q into v minus u divided by v. So, q dash is the effective flow rate, or you can say that resultant flow rate that will be reaching on the moving flat board. Since the change in the velocity in the direction at the right angles to the flat bodies, which will be as v minus u v sin theta, then the force acting on the flat board according to the balance of the momentum equation, you can see that simply what will be the effective mass here, that will be reaching that rho into q dash, and what will be the relative velocity, that will be v minus u into sin theta. So, this will be your simply what is that, if you substitute this q dash, then it will be rho into q into v minus u square by v into sin theta. So, from this equation number 12, we can calculate what should be the force if the board is moving in the same direction at a certain velocity. Let us do an example for this, as shown in this figure here. Here this is the jet, and this jet is divided into two parts whenever it will be approaching to this board, and which will be moving in the same direction at a velocity u. Now, in this case the jet of water of flow rate q and the diameter d that strikes the moving plate of velocity 100 meter per second at an angle theta. Now, calculate the force on this moving plate. In that case, theta again it is given 60 degree, d is 25 millimeter and q is 0.12 meter cube per second. So, what is the difference from this previous problem is that we have not considered that the flat board is moving at a certain velocity, but here in this case flat is moving at a certain velocity, that is 100 meter per second. So, the fluid jet is moving from the mass conservation equation, that will be equal to u, that is equal to 244.46, that is your jet velocity, whereas plate velocity is what u, that is 100 meter per second. So, what will be the effective mass that will be approaching to this moving plate, that will be equal to q into v minus u by v as per equation number 11. So, this will be 0.071 meter cube per second. Similarly, if we calculate this f based on the equation 12, then f will be equal to rho into q dashed into v minus u into sin theta, that will be equals to rho q into v minus u square by v after substitution of this q dashed here. Finally, it will be coming rho q v minus u square by v into sin theta. Now, theta you know, q you know, rho also it is given to you, v is known to you, u is known to you now, v is known to you, everything is known to you. So, finally, after substitution of these values, here we can easily calculate what should be the f, and this f will be equal to 8871.55 Newton, and q 1 again it will be q dashed into 1 plus cos theta by 2, that will be 0.053, and q 2 will be equal to 0.018 here. So, based on this equation you can calculate what will be the components of the mass of the jet that will be moving along with the surface of this moving plate. So, this is your example. So, you can easily now understand how to calculate the force acting on the moving plate by the liquid jet, and also that jet will be balanced by the moving plate by exerting the same amount of force on that, and that will be calculated by the momentum equation here. Another example of momentum equation is that loss in a suddenly expanding pipe. Here see in this diagram, this is the pipe section whose cross section will be certain there, pressure exerting in this pipe whenever fluid is flowing at a certain velocity, that will be V 1, and at these sections here see the diameter of this pipe will be higher than this pipe. So, in this case section 1 and section 2 the cross sectional area will be different. So, in this case A 2 is greater than A 1, that means here this pipe is suddenly expanding from cross section A 1 to A 2, smaller to higher cross sectional area. So, in that case you will see whenever fluid will be moving from these sections, the liquid will be changing its velocity from V 1 to V 2. That means, the same amount of fluid mass will be acting over these sections because of the mass conservation. So, there will be change of momentum. So, based on that change of momentum equation or momentum, we can easily calculate what should be the force acting over there due to the change of cross section. Now, whenever the cross section will be changing, there will be a loss of energy. There will be a certain loss of energy. What should be that loss of energy? First of all, we have to do energy balance over these two cross sections area. Already we have learned how to apply the Bernoulli's equations, that is energy equation. So, if we apply the Bernoulli's equation over these two cross sections of this pipe, so we can have this at these sections what will be the P pressure, at these sections what will be the velocity and pressure there. So, if we have that at cross section 1 and 2, then P 1 rho z plus V 1 square by 2 z that will be equal to as per this Bernoulli's equation here. So, P 2 by rho z plus V 2 by rho z. So, this is up to this if there is no cross section change, but since there is a cross section, then you can easily sudden expansion of this, because of which you will see some changes of energy. There you will not get exactly the same energy what is supplied by these sections here. So, there will be some loss, that loss of course to be considered here. So, that is why this SS term, that is loss of energy, that you are considering here. So, this is actually head term P 1 by rho z, this is head, this is head. So, in this section 1, this is smaller diameter pipe, the total head is this one, and the larger section's total head will be this one, by considering the loss of energy there or loss of head there. So, which will be implying that SS will be equal to this plus this. This is pressure energy, this is kinetic energy here. So, this loss energy how to calculate? Now, from the momentum equation based on this control volume here. So, we can do the balance of momentum here. So, in this case what should be the momentum change whenever velocity is changing, that will be rho q into V 2 minus V 1, and here the force is acting, it will be P 1 minus P 2 into A 2 here, because this momentum, whenever this momentum change, that will be acting over these cross sections. Because of this sudden expansion, this momentum it will be thrusting over this cross section here. Now, at this cross sections what will be the force to balance those momentum change? That force will be equal to what will be the pressure change here, P 2 minus P 1 or P 1 minus P 2 into cross sectional area, that will be A 2 here. Here you have to consider this cross sectional area of A 2, because that momentum is acting over this cross section of A 2. So, that is why you have to consider this the pressure change into cross sectional area. So, again from this mass conservation equation, what should be this velocity V 1 and V 2 from this volumetric flow rate, and then what is that after substitution of this V 1 and V 2, and we can get this equation here P 1 minus P 2, that will be equal to this. And so, by this equation number 15 and 14, we can simply calculate what should be the head loss whenever there will be a certain expansion of this pipe. So, by this equation number 18, we can easily calculate. In this case, we have to know the cross sections of this section 1 and cross sectional area of section 2, and also if you know the velocity at which the fluid is moving from this smaller diameter pipe. So, if it is V 1, then you can easily calculate what will be the energy or head loss over there. So, this SS is called the Borda-Carnot head loss or simply the expansion loss. So, you have to remember this, that Borda-Carnot head loss, or which is called the expansion loss, that you can easily calculate once you know the velocity through the pipe at this cross section 1 and also the cross sectional area of these two sections. Another example of momentum equation like jet pump. See here, this is one jet pump. In this case, one jet will be produced by changing the cross section of the pipe at this location here. Just the liquid will be passing through these smaller cross sections, and then it will be moving over this through this pipe. Now, in this case here, whenever liquid is coming from the other cross sections, and if it is passing through this smaller cross sectional area, there will be a formation of jet, and the jet whenever it will be plunging, that will be plunging over a pool of liquid or some other surfaces, you will see there will be a certain what is that momentum change, and that momentum change will be actually applied for a certain operation, like suppose fluid mixing is there. If suppose in any reactor I want to actually mix the fluid uniformly throughout the cross sections, in that case if we use jet here instead of stirrer, if we supply the liquid continuously through a nozzle, in the nozzle you will see through the nozzle whenever liquid is coming, the liquid will having the velocity that will be higher than the other portion. So, at high liquid jet, whenever it will be plunging over the pool of the liquid or whole mass in the reactor, then you will see that the liquid jet, that liquid momentum will be distributing over the or throughout whole reactor, and that energy distribution will mix whole fluid element in the reactor. So, to get the mixer, to get the mixing of this fluid element, we can apply this jet pump. Sometimes to supply the gas by sucking through this liquid jet. Here suppose any liquid jet is coming in a pan of liquid, and this jet is applying here through a nozzle like this, and here one gap, and here one this provision is made like that. Through this this is called ejector system or one that gas suction chamber. Whenever liquid jet is coming through this suction chamber, and if it is plunging in the pool of the liquid, here you will see the jet will automatically suck this gas and it will carry through this liquid jet, and it will be plunging into the pool of the liquid here. So, this gas is plunging into the liquid jet here. So, and gas will be entrapping or entraining into the liquid here. Now, this gas will be mixing over here. Again another example, suppose if any in any column, suppose jet is applying liquid jet is applying in this column, where this column there will be a mixture of immiscible liquids like kerosene and water. So, in this case if you want to mix this kerosene and water, you have to apply this jet of liquid continuously through the jet, then you can get the formation of jet by mixing of this liquid by breaking its surface. So, for mixing and the formation of droplet, formation of bubble, you can apply this jet pump. Okay. Now, what should be the force applying by this jet to mix this fluid in the reactor or some other applications? So, you have to calculate by this momentum equation. Now, if V0 is the velocity of the jet that discharging here, discharging at a section 1 here, okay, the velocity of the surrounding water is there, and assuming that mixing finishes at section 2 here, there will be a mixing, of this fluid at this section 2, and the flow is then uniform velocity V2, it will moving further, then outflow momentum will be is equal to cross sectional area into density into V2 into V2. That means, here cross sectional area into density into V, this will be your mass, into V, this will be then into V, this will be your momentum. So, according to that in the section 2, the momentum outflow momentum will be equal to pi d square by 4, this is cross sectional area into rho into V2 square. Similarly, inflow momentum will be equal to pi by 4 into d square minus d square here, this will be your total cross sectional area. So, this is your small d. So, small d after subtracting this small d cross sectional area of these two, then remaining portion will be the cross section of this part section 1. So, this will be a cross section, and this will be flowing at the velocity u1. So, this will be rho into v1 or v1. So, plus and then whenever it will be moving this section, then it will be your what is that pi by 4 d square into rho v0 square. So, this will be your total momentum inflow. So, momentum at these sections and at this section this will be given by this, and momentum from this section it will be by this. So, total momentum over this here it will be equal to this 2, and increasing momentum that will be subtracting these 2, then you will get the increasing momentum. Now, this force acting on the fluid by the jet, that will be equal to here what is the pressure pi d square by 4 p 1 minus p 2. This will be your force acting on this. Now, balancing these two equations, okay, we can get by law of momentum simply by balancing these two. So, we can have after rearrangement p 2 minus p 1 will be equal to what. So, from this jet, what will be the pressure creating by the jet pump, that will be equal to p 2 minus p 1. So, this will be your as per equation number 21. So, this equation shows that pressure difference by this jet pump whenever it will be supplying or any applying for mixing purpose, just allowing it through a small nozzle, then the pressure difference can be calculated. So, this equation shows p 2 minus p 1 always positive, since the pressure p 2 will be higher than the p 1 here. So, in other words, the jet pump can force out water against the differential pressure. So, very interesting that main principle is that jet pump can force out the water against the differential pressure. So, this is the law of jet pump. So, what should be the differential pressure, that you can calculate by this equation number 21. Now, another example of momentum equation, that is called how to calculate the efficiency of a propeller. Now, this is one propeller like aeroplane here. So, one here, this is the propeller, and this by this movement of this propeller, the liquid will be moving from this section to this section. Now, at this section see velocity is u, and whenever propeller is applying, some liquid will be throwing from these sections to this section, and the fluid will get some acceleration and getting the velocity higher than this. So, that higher velocity, that means increment of velocity is let it be small u, then at these sections the velocity will be u plus capital U plus small u. So, a propeller of diameter d moving from right to left at velocity u can be considered as the case where a flow from left to right at velocity u strikes a propeller at rest. So, in this case fluid will be forcing in this direction, where propeller will be forcing in this direction. So, this balance will be obtained by this momentum equation. Now, first of all you have to calculate what will be the fluid velocity at this section, that will be u plus u, capital U plus small u, and here this is capital U. There will be certain increment of this velocity, that will be by small u. So, from the changes in momentum and the kinetic energy across the revolving forces by this propeller, and we can calculate the thrust and then what will be the efficiency of that propeller also. Now, in this case what will be the thrust that acting, that will be calculated by the momentum exchange or momentum change, that will be m dot into u 2 minus u 1. So, that will be equal to what? M dot, that is mass flow rate, that will be equal to pi by 4 d square rho u at these sections into increase of velocity, that will be u plus u minus u. This will be cancelled out, and then finally we can get what is that, pi by 4 d square rho u square. Now, the pressures upstream and the downstream should be constant, that will be P, that you have to remember. So, in this case we are calculating how the liquid will thrust on the propeller, and propeller oppositely will also keep the force to balance on this. Now, after that you have to calculate based on this thrust what should be the propulsive power that given by this propeller. Now, power is calculated by thrust into velocity change. Now, this thrust is already calculated by equation number here is suppose this 22A, this is 22A and here this is 22B. So, from this you can then from 22A, if you substitute the value of thrust here and the velocity change is nothing but what is that here it will be u plus u minus u. So, finally, it will be coming as pi by 4 d square into rho u square into small u. The power expended is equal to the power imparted to the fluid, which is the change in the kinetic energy of the flow as it passes through the propeller. So, this is the important point that you have to remember, by which you have to calculate this efficiency of the propeller. Now, power inserted to the fluid is calculated based on the Bernoulli's equation, that will be equal to P imparted, that will be m into that is velocity change. This is because pressure is remain constant and this is horizontal. So, what is that potential head also will be neglected and the pressure head will be neglected. So, only velocity head will be calculated here. So, based on that we can calculate what will be the power. This will be then this is m in dot into u 2 square by 2 minus u 1 square by 2. So, this will be here it will be of course, after substitution of this, then you can get this value and finally, it will be by this equation. Then efficiency will be equal to what? Propulsive power upon power imparted to the fluid here. So, after substitution of this power, propulsive power and this here P imparted by this equation and after simplification, you can get what should be the efficiency of the propeller, that can be calculated by this equation here, that is 2 by 2 plus u by u capital. So, very interesting that if you know only the increment of the velocity whenever fluid stream is thrusting by this impeller and the velocity is having the velocity increment of small u, then what will be the increment small u and what will be the initial velocity of that fluid, from which you can easily calculate what will be the efficiency of the propeller by this simple equation, equation number 23. So, we have applied this momentum equation in the several application like efficiency of the propeller to calculate the differential pressure of the jet pump and also what is that other application that we have discussed here. So, I think we now know how to calculate, how to use the momentum equation, how to use the mass conservation of equation and also how to use the energy equation. So, these three equations, the basic equations of the fluid flow and which are applied in the various fluid flow operations and also for designing various devices based on this principle, and also the designing of that like here jet pump, propeller, all those things. I think this one directional fluid mass is, I think now we can have the idea of the energy equations, momentum equations and the mass conservation equations to apply in the various fluid flow operations in the practical some process industries. Okay. And so, for further I think you can follow some other books also. In this case angular momentum also you can calculate based on this here. So, these slides you can I think go through that how to actually use that conservation of angular momentum here. So, and also these are the some application of this angular momentum, and here from these equations also whenever fluid is flowing through this conduit at a certain angle with a certain angular momentum, then what should be the force acting over there, you can easily calculate from this. And what should be the power there will be, if there is a wheel or pump there, that also you can apply the momentum equation here, and based on that, if you are considering here that what should be the torque whenever fluid is actually discharging by the pump, then how what amount of actually torque is applied by this wheel of this pump, then you can calculate from this equation. And if you know the angular velocity of the impeller, the power L, you can calculate from this equation torque into angular momentum here. So, W is the angular velocity. So, here this T into omega, that will be your angular momentum, and then you can calculate this power based on this. So, for further reading, I should actually suggest this other textbooks of this here given in the slides. So, thank you for giving attention for this lecture. Thank you.